Dwyer. I'm the session moderator. Again, just as a quick recap of the guidelines, you guys have 15 minutes, followed by 5 minutes of Q&A. We're going to start with judge Q&A, and we can switch to audience if we have time. I'll just pull these up for minute markers. Other than that, you guys are good to go.
Oh, time left.
Yeah, so 5 is
good. Great.
Start with Eddie.
Okay. Hello, everybody. We are Team Fred, the robotics competition team from Front Range Community College. Today we're going to be presenting our research benchmarking machine learning algorithms for autonomous rover control on a resource-constrained platform. My name is Jasper, and these are my associates.
Madeline Kamanda.
Kevin Martinez.
Zoe Woodward.
The goal of our research was to find out which machine learning platform performed the best when embedded on a system with limited power and compute like a Raspberry Pi. We compared average course completion time, number of incidents, CPU and memory usage, as well as power draw to evaluate performance.
The importance of our research extends to demanding environments. This could be places where it's too dangerous for humans to explore, such as in space, in other planets, where there's limited power and the robot must be autonomous. Our findings contribute to AI research. Currently, there's a lot of research that's being done on hybrid models and comparing deep learning models to each other. However, our research focuses on comparing reinforcement learning to deep learning. This will also help in the field of robotics to help developers choose the best machine learning framework based on their hardware and goal constraints. Now, let's walk through how we actually collected this data to test our models for effectiveness.
I'm trying.
To ensure statistical reliability and stability, we kept the hardware the same throughout the research. This ensures that for each test run, the only variable was the machine learning model. This was to ensure and be confident that, so we could confidently attribute the performance differences to the machine learning models themselves. The hardware consisted of a Raspberry Pi 3, Arduino Nano ESP32, 4 ultrasonic sensors, 2 IMU sensors, 1 time-of-flight camera sensor, and 4 total motors, and 2 H-bridge motor drivers to control this.
So for our data collection process, all of our models started out with connecting the Raspberry Pi to a PS4 gaming controller. For our deep learning models, PyTorch and TensorFlow, we manually drove the rover around the obstacle course, logging data from the sensors, camera, and motors to a CSV file. We then uploaded that file to a Google Colab script to train the model, which is a cloud-based coding environment that allowed us to train the model much faster than only using the Raspberry Pi. We then created the inference script to run the AI model on the robot. For Q-learning, we started with having the robot on the obstacle course and making a random action. We then used the PS4 controller to provide feedback, either a reward or a punishment, and have our feedback stored in a Q table that's then loaded to the inference script. The Q table stores a value of a specific motor value into a specific situation. So for our obstacle course, we had 2 obstacles on each side for the 5-meter long obstacle course. To ensure consistency, we had each of the 6 machine learning frameworks for our models run a total of 10 times. We recorded the time it took for each model to complete the course and the number of collisions for each run. So for our machine learning frameworks, I'll begin with TensorFlow. We used a convoluted neural network to look at the camera's depth image to detect patterns and specific features. Then we used dense layers to process all of it and combine it. Pruning was used to remove weights that were unnecessary, which is a number that tells the model how important the input is. So this removed the small weights or ones that are only used a couple of times to make the model run faster and more efficiently by minimizing the processing requirements. Both TensorFlow and PyTorch save the last 10 rows of the data. This provides the model with more context to create a short-term memory. They also train in similar methods. So the data from the CSV file is split into 2 parts, one for training and one for testing. This ensures that the model is tested on completely new situations that still from the data. All 3 of our models use something called action stickiness. This is where the model must predict the same motor commands prevent erratic movement. For PyTorch, we used a dual branch neural network architecture. So the first is a convoluted layer like TensorFlow that's used for the camera data. And then we use the dense layer to process the sensor and heading data. Now, for Q-learning, there's no neural network. It's reinforcement learning, meaning it learns through trial and error. So Q-learning looks for three things. It looks for the state, which is the situation the robot is currently in, the action, which is the movement it must take, and then the reward. If the rover crashes into something, it'll receive a negative reward, and if it successfully avoids an obstacle, a positive reward. So we use the same Q table from training for our final inference script. To make this more manageable, we applied a rolling average and a frame buffer for the camera. We also separated the camera into three sections, left, middle, and right. Then we created thresholds to convert the data into discrete categories or bins, which allowed us to represent the environment as a simplified state for Q-learning. This simplified the data into close, medium, and far. Now that I've introduced how each machine learning framework functions, we'll explain the 6 models we built.
So this chart shows how the 3 machine learning frameworks were trained and tested. The 2 deep learning models were both trained with 2 datasets. The first one was a larger outdoor dataset, while the second one was a smaller, more course-specific indoor dataset. This was intentional so that we could examine not just the efficiency of the frameworks, but also how important it is to match the training environment to the deployment environment. Q-learning was run twice to validate some invalid data that we'll talk on here. Now let's take a look at how the frameworks actually perform. But before that, our team hypothesized that TensorFlow would work the best all around due to it being more developed and optimized for edge computing.
Taking a look at the actual data. First, I'd like to just acknowledge how the graph is structured. The following graphs, there's a few of them, all share the same structure. This laser's so cool. PyTorch, PT, represents the full-sized PyTorch using 40 megabytes of data collected over various outdoor and indoor courses. PyTorch Indoor, PTI, there it is, uses only the indoor course-specific data. It's only about 3 megabytes of data. This is something that Kevin just touched on. The same can be said for TF and TFI, while QL and QLI share the exact same framework, which makes sense as the data is relatively similar between the two of them. So the framework for Q-learning stays the same. Now, let's move into what the actual data says. This is something that we're going to be calling real-world performance metrics, which is to say how quickly the rover completed each of the demonstration research courses. They were 5 meters long. On the left side, the blue bars represent course completion time in seconds across each model, while the red bars on the right represent the number of incidents that each model incurred. This is to say the robot hitting a wall or obstacle over the duration of the course. You can see here that TensorFlow, specifically the small indoor dataset TensorFlow TFI, performed the best across both metrics with quick completion times and very few incidents. Following suit is Q-learning with moderate completion times. Q-learning did, however, have very few incidents, likely driven by the reward policy in training. The robot recognized very strongly that it was given a punishment if it got too close to an obstacle. PyTorch underperformed in both metrics, likely due to the model size and complexity not being optimized for the Raspberry Pi. Next, let's move into CPU and memory. Memory usage does not vary in any significant way across all of our trials. However, the same cannot be said for CPU usage. TensorFlow Lite, specifically the TFI, outperforms both Q-learning and PyTorch, likely driven by the highly optimized TF Lite as opposed to a full-size TensorFlow model. Q-learning follows suit with a mediocre performance. This is likely driven up in CPU usage because of how often Q-learning has to reference the Q table where it gets all of its decisions from. PyTorch, again, underperforms in both metrics, likely because of its complex, large model size that hasn't been optimized for the Raspberry Pi. More informative than just raw CPU and memory usage is the overhead that each model introduces on top of the Pi's operating baseline. We set the pi down for 10 minutes, and every second recorded how much CPU and memory was being used at that time. We calculated this average, and we take it away from the raw data in both situations. Again, you'll notice that memory does not vary very much. In one case, it even was underneath the baseline, although very little. The CPU again represents, the CPU again demonstrates that TensorFlow-like performs better than both Q-learning and PyTorch. Power draw over the course of the trial is very similar, and here we actually, the most significant thing is the first Q-learning trial had this both erroneously high but also inconsistent data as demonstrated by the large error bars, prompting a second Q-learning trial to validate the first data. We believe that the first data's inconsistencies are due to a number of things like background tasks running on the Raspberry Pi, and if we were going to do it again, we would like to measure that, but we didn't for the sake of this research. Moving right along into analysis of this data.
Analyzing our results, here's some key comparisons we found. As you can see, TensorFlow Lite was the most efficient with CPU usage at 18.98% above our baseline, and ran the course the fastest at just under 40 seconds. Q-learning had a larger impact to the CPU at 66% above our baseline, and ran the course in a moderate 60.8 seconds. And then PyTorch came in last with the highest CPU usage at 72.1% above baseline, and the course was ran at a sluggish 65 seconds. When we compare our power versus performance, you can see that TensorFlow, PyTorch indoor, and Q-learning indoor had lower energy usage, but significantly slower completion times for the obstacle course. Q-learning had the highest energy consumption, but had a moderate completion time, and TensorFlow was among the most efficient and ran the course in the fastest time. The consistent performance of TensorFlow Lite across all 10 trials taught us something surprising. It's that the model fit matters more than the model size or complexity. In all of our research, we read repeatedly that when it came to deep learning networks like TensorFlow, the more data, the better. However, what we found was that if it was trained on smaller, more relevant data, it outperformed all of the other models, including the more complex TensorFlow, PyTorch, and reinforcement-based Q-learning. We found that TensorFlow Lite is ideal for embedded systems given processing and power budgets. Q-learning would be more viable if we had a greater power budget, and unfortunately PyTorch requires more computational resources than we had available.
For our areas of improvement, I'd like to note that while the research was thorough and insightful, none of us are experts in machine learning or data scientists. If we had more time, we'd like to focus on gaining a deeper understanding on how all of these models function. We'd also like to collect more data to help us better understand and explain the inconsistencies, such as those that we saw in the first Q-learning trial.
There's still a lot of more work that could be done to the rover and the research. This could include adding more cameras to have better sense of where it's at, having stronger processors. We could also have like a flatline detection to sense when sensors stop sending data, or even compare hybrid models with Q-learning and TensorFlow together.
I'd like to just take a brief moment to explain the fact that all of the graphs, statistics, and diagrams in this presentation can be found in our research paper. All of our source code for this project and research is linked and in the GitHub repository. Many photographs inside of this presentation were used courtesy of the Google Slides stock photograph library, and many photographs were our own. Thank you all so much for watching.
All right, so we'll now turn to 5 minutes for Q&A.
All right. Great presentation. I like the way you attacked the problem. Same piece of hardware, different software, different models on the software side. you expect the results to be any different if you had a different robot to work with?
I think the key metric there, there's two things. Number one, this robot's very slow. It's designed to be very slow. It has powerful wheels. It can get over rocks at the sand dunes. The cumulative power that the robot uses is a function of how much power the processor is using over time, right? So a faster robot is going to have to think for less time to get through the same distance. That's the biggest difference, I think. And the other one would be the sensor array might change on a different robot, which would prompt different algorithms to perform in better or worse ways.
Thank you. Yeah, I don't think I have any other comments. My knowledge of some of the software in the Raspberry Pi is very limited. I would make one comment. I think I liked watching your slides. I had enough time to look at them, with the exception maybe of the first slide, which was kind of a nice chart. That you could maybe break it down to a couple bullet items. That would be a little easier to handle. Other than that, we go to.
Yeah, and then we've got another judge that joined us on Zoom. So Nicholas, if you have any questions.
Nope, the one question I have is about the usage of the software with different rover designs. So that was answered. Yeah, very good presentation.
Okay, sweet. And then we've got about 3 minutes for audience questions. Anyone's got any? Yeah.
I saw your hand first.
Cool. I was curious how you implemented the positive and negative feedback. Was it based on like closeness to obstacles or like meeting waypoint requirements? How did you guys determine that?
We tried that first, but changed it up a little bit.
Yeah. So what we ended up doing was using the gaming controller. We would have that connected, and while the rover was, so it would make one action, and using the controller, we'd hit X to punish, O for a reward. And if it did get too close to an obstacle, it would first move and then wait for our feedback. We'd reward or punish, and then it would make another action. And then over time, it learned by saving the table.
We did try to do a hard-coded, like a reward function for a while, and the sheer amount of variability in the state space made that really hard. So, remote controller. I saw a hand over there. I think yes.
How did you decide to set up the obstacle course the way that you did?
Well, we really wanted to emphasize the overhead that each different model introduced, and not give any model an edge over the other. So the course was designed so that it could be run 5 times one way, 5 times the other. It was an equal length every time. It was indoors, so the ground was the same, the lighting was the same. And we had 2 obstacles on each side, so it didn't favor one side's sensor array over the other side. Yes?
So I might have missed this, but you guys talked, it took like around 50, 60 seconds, depending on the model, to like complete the entire course. So I was curious, if you were to like run the distance of the course with just like a straight line, like do you know how long it would take your robot to like complete that time? Just so that like how close you are to like the optimized amount of time that it would take to complete that course.
Right, so like I just mentioned with the 2 obstacles on each side, we can go back a little bit. The course was designed so the robot could not go in a straight line. It had to navigate around this one and had to navigate around.
Yeah, so what I meant was like if you took like the most optimal path, right? And just like, let's say you pre-coded the most optimal path and it just ran, do you know how long that would take just so you can compare it and see like which model could get the most efficient?
Yeah. I saw a hand in the back.
And that'll probably be our last question. But
Okay.
At one point you mentioned having these 2 data sets, right? You have the indoor data set and you have the bigger outdoor data set. Did you ever consider using fine tuning to train it on motion on the outdoor data set and then a more specific fine tuning on the indoor?
What kind of fine tuning?
I mean, really, I'm also not a machine learning expert, but I am aware of the ability to fine-tune models on specific data sets after they have been trained on a much larger data set. You know, you see GPT being fine-tuned on medical data sets, stuff like that.
We could have, you're right. Taking the indoor specific data set and using that to prune the larger outdoor specific data set. For the scope of this, we really just wanted to compare the deep learning to the reinforcement learning and did not end up doing that. In retrospect, that might have been a good idea for the dunes. Still did pretty well, but yeah, it's a good idea, I think.
But also from what I've read in different articles, a lot of the fine tuning is also done with reinforcement learning. So like it's done with hybrid models with deep learning and reinforcement learning.
Okay.
Sweet. All right, well, one more round of applause. Good job, guys. And then we got one more presentation in this room.